Making molecules, mass to mass conversions. So when we made pancakes, we counted eggs and we counted pancakes, right? And that works out really well. It doesn't work out so well with atoms and molecules because they're so tiny we can't see them, and there's so many of them that we can't count them. How did we learn how to count atoms? By weighing. Just like you can count nails by weighing, you can count atoms by weighing. And so what we need here is a mass to start with and a mass to end up with, so that we can count them by weighing them. The chemical equation gives us relationships between moles of reactants and moles of products. But we're more interested in mass of reactants and mass of products. And so this is our big picture path of what's going on. The mass of what you're starting with to moles of what you start with, to moles of what you're trying to find, to mass of what you're trying to find. This in the middle is what we just learned how to do. Moles of one thing to moles of another. We already learned how to do this. That's a conversion using the molar mass of the element or the compound as a conversion factor. And then at the end, from moles to mass, we use the molar mass again. So we're going to take two things, one on each end, skills that we've already learned, and we're going to add them to this new skill. Now, the way I usually think of this is a little, choose a pen first. Come on. Grams to moles to grams. And Dora remembers the path that the map tells her by repeating it over and over again, right? This is our little mantra for stoichiometry. Grams to moles to moles to grams. Grams to moles to moles to grams. We never ever do moles to grams to grams to moles. It never ever works that way. Moles to moles is always in the middle. And you know that you've chanted this enough if you wake up muttering it in your sleep, right? Grams to moles to moles to grams. Okay, this is the path. Okay, let's look at this one. Here we have the equation, the chemical equation describing the combustion of octane. We've now talked about combustion reactions, right? This is a hydrocarbon, and it's reacting with oxygen, producing carbon dioxide and water. This is the balanced chemical equation for that. So we can answer a question like this. What mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2 grams of pure octane is burned? So I'm going to use the chemical equation to organize the information. The question is, what mass of carbon dioxide? So under the formula for carbon dioxide, I'm going to write question mark grams. If they don't tell you what the unit is, it's for mass, we would use grams most of the time. And then here's this number, and that's pure octane. So that's this guy over here. I wouldn't expect you to recognize the formula of octane, but I would expect you to know that this is oxygen, that's carbon dioxide, and that's water. So octane has to be the other one, right? So this is 5.0 times 10 to the 2 grams of that. Now, can I use these coefficients? Do those mean that 2 grams of this makes 16 grams of that? No. 2 moles makes 16 moles. We have to go grams to moles to moles to grams. We can't go grams to grams. Grams to moles to moles to grams. So let's write the path out here. Grams of C8H18 to moles of C8H18 to moles of what we're trying to find, moles of CO2 to grams of CO2. Grams to moles to grams. This relationship in the middle is what we get from this 2 and the 16. The grams to moles is going to involve a molar mass, and the moles to grams is going to involve a different molar mass. But we've got our path, and now we're going to write out all the units so they cross out and work out the way we need them to. So grams to moles to grams. So we're going to start over here. 5.0 times 10 to the 2 grams of C8H18. My path has 3 arrows. It needs 3 conversion factors. So the next one is moles of C8H18. Apparently I write faster than my little iPad mini can handle. So that's this guy. The next one is moles of CO2. And the final one is grams of CO2. It's all about the units. I'm going to take this unit and put it in the bottom. I'm going to take this unit and put it in the bottom. I'm going to take this unit and put it in the bottom so they'll cancel out. Is everybody okay with that? Now I need units. I have units. I need numbers. I like to do the easy one first. The mole to mole ratio in the middle is the easy one. That's the one we just learned how to do. We just go up here and look at this chemical equation. There's a 2 in front of C8H18. So down here in front of moles of C8H18, I'm going to write 2. What number is in front of CO2 in the balanced chemical equation? 16. So I'm going to write 16 here. Now some of you might think, well, 16 over 2, that's 8. You could simplify that if you want to, but my experience is I occasionally have a brain fart when I do stuff like that, and I do it wrong. We're going to have to use our calculators anyway, so I'm just going to multiply by 16 and divide by 2, and it'll be right then. I'm not going to worry about it. The relationship between grams and moles, that's the molar mass. So we have the formula, we have periodic tables. So we look at this formula, C8H18. I'm going to do this in a different color down here so we don't get too confused. There are 8 carbon atoms, or 8 moles of carbon in 1 mole of this compound. And so that's 12.01. And there are 18 hydrogens times 1.008. I'm going to do that on my calculator. And my calculator says 114.224. Grams of C8H18 is equal to 1 mole of C8H18. Keeping track of sig figs, this would have 4. But I want to keep those extra digits because I don't want to round stuff off until the very end. So that number goes in here, 114.224. I put it in the denominator because it's the number of grams. The unit gram is in the denominator and the number has to go with grams. That's equal to 1 mole. So if I want to, I can write a 1 up there. 1 mole equals that many grams. Then I need to do a similar thing for the CO2. Well, that's 1 carbon and 2 oxygens. Yeah, because I did that and it came up 14, and I know that's not right. I put the mass of hydrogen in there. I don't know why I did that. That does illustrate a point, though. It's good to have this written out, because then if you do something stupid like that, you can go back and say, oh, duh, that was wrong. 44.01 grams of CO2 is equal to 1 mole of CO2. Do you remember calculating molar masses? It wasn't that long ago, hopefully. So, 44.02 grams of carbon dioxide. There's grams of carbon dioxide. That's where the number goes. 44.0. I said 2, didn't I? 1. 44.01 to 1 mole. Now, we use our calculators. Just start at the left, multiply by the top, divide by the bottom. Times the top, divide by bottom. Times top, divide bottom. And that way you won't forget anybody. So that equals, I'm going to write it up here because I ran out of space. My calculator is showing me 1541.1822 blah, blah, blah. Did your calculator give you that number? How many significant figures should I report in my answer? 2. This has 2. This is exact. That's got 4. This has 4. So, is it 15 grams? No, it's 1,500 grams. This is the last significant digit. That's in the hundreds place. That means I'm rounding this to the nearest 100. The nearest 100 is 1,500. So that would be an okay answer. The best thing to do, though, is put this into scientific notation, 1.54111822 times 10 to the what? 10 to the 3 grams. I'm going to keep the 5, 2 digits. Now when I round this, sorry, I'm going up and up and up, 1.5 times 10 to the 2 grams of CO2. That's the best answer. This is okay. Any questions? Yes, thank you. I was trying to see if you're paying attention. I like to make myself feel better sometimes. Yeah, because when you just recopy it, you don't change the exponents. Okay. Any questions? The individual steps aren't hard. It's the putting them together, remembering what you're doing, where you're going, that can be challenging. And the way to get better at it is to practice and practice and practice. But you need to make sure you're practicing correctly. That's what the homework's for, and worksheets. Let's do another one. Same equation. What mass of octane would be needed to generate 42.3 grams of water? Because we can look at relationships between any two of these substances. Again, I'm going to use the equation to organize my answer. organize my information. So how many grams of this would be needed to make 42.3 grams of water? This time I'm starting with a product and I'm working this way trying to figure out how many grams of that. So I'm going to write out my path. When you're first starting with this, you should write this path out. Later, when you feel like you know what you're doing, you can just do this in your head. So grams to moles to moles to grams. Grams of water to moles of water to moles of octane to grams of octane. This is my starting compound, grams of that to moles of that. This is what I'm ending up with. I go to moles of this and then to grams. Any questions? Once you get this in place, then it's just dimensional analysis. Okay, so 42.3 grams of water times what unit goes on the numerator on the top of this fraction? Moles of H2O. And then the next one, what goes on top? Moles of C8H18. And what goes on top of the last one? Grams of C8H18. Grams to moles to moles to grams. I take this unit and I bring it down here. Grams of H2O. So that those will cancel out. The next term I want to divide by moles of H2O. So the moles of H2O cancel out. And then this last one I've got moles of C8H18 in the denominator, and that will cancel with this one. When I do these calculations, even just quick and dirty for something I need to know in the lab, I put the chemical formulas and the units in there. Because it's not faster if you leave them off and you get the answer wrong. It's a lot slower, actually. So I know it's a little tedious sometimes, but write the unit and the chemical formula every single time in these equations and make sure that they're really canceling out and not just you're hoping that they're going to do that. The middle one is the easy one. What number goes in front of moles of C8H18? 2. And in front of moles of H2O? 18. That's this. 2 of these make 18 of those. Those are the numbers that go in here. Now we need the molar mass for water. I happen to know what it is, but we'll calculate it anyway. 2 times the mass of hydrogen plus 1 times the mass of oxygen, 18.016 grams is 1 mole. This one we calculated on the last slide. 114.224. Is that what it was? And the significant digit was there. So any questions about where I got those numbers and how I knew where to put them? Now we multiply and divide. 42.3 times 1 divided by 18.016 times 2 divided by 18 times 114.224 divided by 1 equals 29. This should have 3 significant figures because of where we started. 29.8 grams of C8H18. If you wanted to make 42.3 grams of water, you would need to combust 29.8 grams of octane. Any questions? Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, which is primarily HCl, hydrochloric acid, according to this reaction. So MgOH2 plus 2HCl forms 2H2O and MgCl2. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? Okay. Just as a little review of Chapter 7, what kind of a chemical reaction is that? This one. Acid-base, right? Acid-base or a neutralization reaction. Okay, so how much HCl in grams? That's the question. Question mark grams under the HCl. And then here's a mass of MgOH2, so I'm going to write that under that formula right there. That tells me where I'm starting, where I'm ending up. Grams to moles to moles to grams. So grams of MgOH2 to moles of MgOH2 to moles of HCl to grams of HCl. Grams to moles to moles to grams. We have the path written out, then we can write the equation. 5.50 grams of magnesium hydroxide times moles of magnesium hydroxide. And then we're going to have moles of HCl. I'm just following the path that I set out. Grams magnesium hydroxide to moles magnesium hydroxide to moles of HCl to grams of HCl. Grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl to grams of HCl. Wouldn't this make a fabulous Dora the Explorer episode? Can you imagine? That might be fun to make for, a YouTube skit or something. So I need this unit down here. Sometimes it's tempting to take shortcuts or something. Don't. Just don't. When something works, don't fix it. So moles of MgOH2 down here. And then I'm going to have moles of HCl down here. Get all the units in place. This middle mole-to-mole term is the easy one. Let's do it first. What number is in front of HCl in the equation? 2. So this 2, I'm going to write in front of HCl in my ratio there. What's in front of MgOH2? An implied 1. And so I'm going to write 1 here. I need to calculate 2 molar masses. So let's do this one first. So magnesium hydroxide, magnesium 24.31. Now let's do a different color. So magnesium is 24.31, and how many oxygens are there? 2. 2 oxygens, and 2 hydrogens. The parentheses here mean there's 2 of everything inside. So 2 hydrogens and 2 oxygens. I said the words backward, but I think you know what I mean. 24.31 plus 2 times 16 plus 2 times 1.008 equals 58.326. So 1 mole of magnesium hydroxide weighs 58.326 grams. And then I need the molar mass of HCl. It has 1 hydrogen and 1 chlorine. So that's 36.458 grams is equal to 1 mole. So 36.458 to 1 mole. Yes?
What different would it be? Because you like for the hydrogen you put the actual 1.008.
Mm-hmm.
Like 1.01.
If you put 1.01, it's probably not going to make a difference in your final answer. Just remember, if you're scribbling to write all this down and having trouble with that, remember these videos are posted on YouTube, and you can go back and watch it again and again and again if you need to. And one of the reasons that I love using Doceri is it forces me to write while you're writing, and it slows me down, because if this is all typed out, we can go way too fast, and it's not a good thing. So 5.5 times 1 divided by 58.326 times 2 divided by 1 times 36.458 divided by 1. Based on the number of significant figures in my initial mass, this should have 3 sig figs, so it's going to be 6.88 grams of HCl. Okay? We doing okay? Kind of? A really helpful studying strategy is read the book, do the pre-lecture questions before you come to lecture. Pay attention in lecture, take notes, go home, read the chapter again, and then all of these, this is Skill Builder 8.2. That is in your textbook. Go back and do those skill builders and see if you can do them without looking at any notes and get them correct. The answers are in the back of your book. If you can't get it correct, go to the YouTube video. Find the section in the video and watch and pause. Watch and pause, watch and pause. Okay? It's a good way to learn how to do something. Another example, mass-to-mass conversions. One component of acid rain is sulfuric acid, which forms when sulfur dioxide, another pollutant, reacts with oxygen and rainwater according to this reaction. This is all very interesting, but not necessary for the problem. Here's the, yeah, it does say kilograms. Here's the balanced chemical equation, and here's our question. Assuming that there's more than enough oxygen and water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the third kilograms of SO2? Don't be alarmed. We know how to convert kilograms to grams, right? There are several different ways you can do this problem. I'm going to do the way that's maybe a little longer, but is more straightforward. Okay? So let's just do what we've been doing and organize our information. How much sulfuric acid? So the question is, how much of this in kilograms? And then what they're giving us is the mass of SO2 also in kilograms. 2.6 times 10 to the third kilograms of that. Well, what we've been doing was grams to moles to moles to grams. Let's convert this to grams before we do anything else. I'm going to do that way up here on top of the slide. 2.6 times 10 to the third kilograms. I'm going to do this the long way in case you don't remember exactly how to do this. I want grams, and I need to divide by kilograms to do that conversion. Then I ask myself, what does kilo mean? 10 to the 3. So kilo is in the denominator. I don't want to write what it means next to it. I want to write what it means on the other side of the line. So 10 to the 3 up there, and that's 1 times 10 to the 3. So when you multiply that out, you're going to get 2.6 times 10 to the 6 grams of SO2. Okay? So I'm going to write that in here as well. 2.6 times 10 to the 6 grams. That's what they gave me, but I converted it, and this is what I'm going to use in my equation. So we're going to go grams to moles to grams, and then we'll convert that answer to kilograms for our final answer. So this is adding a step on each end, and it's not that bad. So our path, grams of SO2 to moles of SO2 to moles of H2SO4 to grams of H2SO4. Grams to moles to moles to grams. Uh, 2.6 times 10 to the 6 grams of SO2 times moles of SO2 over something times moles of H2SO4 over something times grams of H2SO4 over something. The path, grams to moles to moles to grams. Grams, come on, grams to moles to grams. So the unit in the first term becomes the denominator in the second term. Moles SO2 come down here so that they cancel out. Moles of H2SO4 come down here so they cancel out. The mole-to-mole ratio comes from the balanced chemical equation. There's a 2 in front of H2SO4, so I'm going to put a 2 there. In front of SO2, there's also a 2, so I'm going to put a 2 there. If you want to cancel those 2's out, you can do that. If you want to multiply by 2 and divide by 2, you can do that as well. You'll both end up with the same answer. Okay, so here we need the molar mass of sulfur. Instead of writing this all out, I'm just going to talk through it. So we have 1 sulfur, 32.07, plus 2 oxygens, 2 times 16 equals. So that's 64.07. And then for sulfuric acid, H2SO4, there's 2 hydrogens, so 2 times 1.008, plus 1 sulfur, 32.07, plus 4 oxygens, 4 times 16. And that comes out to 98.086. If you need more examples of calculating molar masses, go back to the chapter where we talked about that. I think it was chapter 6. So So on my calculator now, 2.6 EE6 times 1 divided by 64.07 times 2 divided by 2 times 98.086 divided by 1, and I'm getting a really big number. Is that okay? Well, we started with a really big number. That's 2.6 million grams, right? So let's not be afraid if we sometimes get really big numbers. Okay, so what I'm getting there is 398.0390.198 grams of sulfuric acid. This is what I got.
I can't, because the first one, we did it, we got the same one, but the decimal was different. So I don't know if it's mine.
So anybody else want to pitch in? We're having a disagreement about a decimal. Okay. I suspect that you did times 10 EE. And that's a common problem. Remember, when you're doing scientific notation, this is 2.6 EE6. EE stands for times 10 to the. Okay? If you're off by a factor of 10 on lots of your numbers, it's usually a scientific notation problem in you communicating with your calculator. And that can cause you a lot of points on an exam. You can lose a lot of points that way. Okay, how many sig figs does this number have? Should it have? How many does this one have? 2. So this one should have 2. This looks like a really good candidate for scientific notation, doesn't it? So this would be 3.98, that's not an 8, 980 blah, 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 times 10 to the what? 1, 2, 3, 4, 5, 6, times 10 to the 6 grams. So that would round to 4.0 times 10 to the 6 grams. Now, is that the answer to the question? No. We need kilograms. So we need to convert. This time I have grams on the bottom, kilograms on the top. Kilo means 10 to the 3. And the grams cancel out. So this, let's write it up here. Oh, let's go a little further. This is going to be 4.0 times 10 to the 3 grams of sulfuric acid. Any questions? Yes? Yeah. Thank you. Kilograms. Yeah. Thank you. Anything else I messed up? I can take it. Okay, let's see what's next. Let's see how many. Yeah, there's too much of that. Well, no, there isn't. We're behind. We're going to keep going.